All right, so what we're going to be talking about here this session, obviously a mini tutorial, so this is going to span about 90 minutes or so, and gives us enough time, I think, to dive into some topics that we feel are pretty important. Big picture on this is that we're looking at statistical methods, as you can see in the title, particularly methods that help in terms of V&V in particular for modeling and simulation. Has been expressed already in the conference, heavy modeling and simulation emphasis. So we're just trying to keep with that theme and talk about a few topics. The way that we have this broken out, notionally 50-50, we'll see, Jim, how it goes, but is for me to cover the first half, basically going over sort of the status quo, current state of application of statistical methods, some on the analysis side, and certainly some on the design side for M&S. Not getting too deep, obviously, in the time that we have, but covering sort of the waterfront to allow Jim then to take the last 45 minutes, the real meat of the presentation, and dive into some newer methods that are available out there, particularly on the analysis side, but also thinking about spanning some new set of that operational space based upon what we learned from initial testing. And so he'll get some more into that as he moves along as well. We'll try to pay attention to chat, although I'm not sure I have that up on my screen, but maybe I'll figure that out as we go along.
Sarah's got us covered.
I'm sorry?
I'll keep an eye out for you, Jim.
Okay, all right. Sarah's got it. Very good, thank you. And then, yeah, and just dive in with questions or comments as you have them. That should work for rules of the road. And we'll probably have a few more administrative comments as we go, but let's go ahead and get into the material. The way this is organized is, like I just mentioned, a part one and a part two. That, again, focusing on modeling, simulation, verification, validation. We're gonna be looking at a couple of definitions right up front, so hopefully clear the air there. But probably most of that content are things that you know already, but never know with the audience, can be quite diverse. So when we talk modeling and simulation, what are we saying? What are we referring to? And the references here largely are based upon Department of Defense, but throughout the discussion that we have, with a few exceptions, you see one here on this slide. But DoD directives, DoD instructions provide us with this one sentence that comprises development and use of models and simulations. Go figure when you're coming up with the definition of M&S. Right, but that's sort of the what. The how is really talking about using models, including what we'll be talking about here as well, emulators, prototypes, simulators, as well as stimulators. So on the front end, trying to interrogate the underlying factor space or input space, if you will, while using stimulators, either statically or over time dynamically. Trying to develop data for making important informed decisions, right? So that's really the how part of it. And then sort of the why piece, Averill Law, great book on simulation and great contributions to industry as well. But saying that trying to use computers to imitate or simulate operations of various kinds of real world facilities or processes. Right, and as we're developing more complex and more advanced and more system-based kinds of technologies that we need, not necessarily just in DoD, but NASA and elsewhere, other government entities, that we're going to lean, and we are leaning more and more heavily on modeling and simulation to make acquisition decisions, to make accreditation decisions, right? So So the need for these kinds of techniques, the need for evolving these kinds of techniques, critical, right, to what we're doing. V&V or VV&A, if you will, verification, validation, accreditation, more formal definitions from the DoD Instruction 5061. Highlighted there are really what distinguishes the three apart from each other. Verification, we're trying to accurately represent some conceptual description. What we're intending to do is the verification. Are we doing what we intended to do? Validation, of course, the accurate representation of the real world. Is it really the true underlying system that we're going after? And then accreditation is sort of the approval stamp that is acceptable for use. We can boil the VVAs down into simpler descriptions, right? Or questions. Building the product right. Is it according to what was intended? According to requirements, a lot of times is one way to be thinking about it. And then validation, thinking about the right product, thinking about whether it's real world is an accurate representation of reality. And accreditation, of course, is it credible to make an informed decision? So that, again, key in modeling simulation. Once we have developed and evolved and matured a simulation far enough into saying it's ready for assessing the underlying system, then it's that accreditation decision so that we can go forward and use it in developmental tests, use it in operational tests as part of answering the question about whether we're satisfying the needs across a bigger space than we could ever cover in live testing. So a lot of obviously basic sort of things there. Basic also in terms of processes to be thinking about is what is the process flow, if you will, for an M&S. And the process flow is not have a starting block and an ending block necessarily. It has a loop, and you see that here as well. That we're going to combine some model or simulation of a system under test. We're also going to be modeling and simulating the environment, and that can include not just physical environment, but many sort of outside influences that could be part of the underlying system. The decision-making process can be sequential. It can be automated. There are a lot of parts of the decision-making that can be involved that needs to be modeled, and then whether other systems are involved, critical systems like in DoD, the threat, and that type of thing. So all those part of the integrated simulation or model feed into requirements, and then the requirements become the assumptions and limitations of the simulation. When the simulation gets more and more developed, then it establishes capabilities, and then at some point we're going to go through the V&V exercise. And note that this is an iterative, all parts of this iterative. So the V&V goes through various different stages as well. There's certainly a plan, again, across most organizations and most philosophies on how you do it. And then there's a reporting out on the V&V. And then in terms of an actual M&S capability, what do we intend to use the M&S for? Do we have the ability to do that? And then what are the acceptability criteria in terms of looking at using that simulation for performance or other purposes? Last sort of introductory slide before we dive into the analysis, statistical methods, and the design sort of components is to be thinking about the things, a couple of things that I just mentioned, where V&V is there at the core. And what are the things that are involved? We got to lay out and describe and agree upon the intended uses of the simulation so that we can assess it from a verification validation perspective. And then get into what are we going to use to determine whether or not we're meeting the intended uses, the acceptability criteria, what sort of data do we need, what form is the data going to be in, what do we do with the data once we have it, and then how do we use that to make informed decisions about V&V and accreditation. All the while, big picture umbrella with regards to documentation important along the way. All right, there's a preamble preface. sort of set up those that haven't been involved in M&S but know statistical methods well will be quite comfortable in this next section. Those that know M&S very, very well, and maybe not the statistical methods as much, might be seeing some new things upcoming, but maybe hearing about some things and then getting a little bit more insight. So some of the methods that come along when we're going to be using some referent for the modeling and simulation in order to determine whether we're valid, whether we can verify certain requirements and that type of thing. And so tests that come sort of filter the top when we just have low amounts of referent data, not necessarily tied to what we call in DOE factors and levels, but we have some information that we want to be able to compare to the simulation. And one way to do that is to look at, say, some measure that we're using to assess goodness of the simulation. And we want to compare the live or the referent to the simulation. So mu1 might be associated with the simulation, mu2 might be an average associated with the referent or the live. And we want to see whether or not we're getting the same result for certain conditions. And so we find ourselves in what we call hypothesis testing, right? To make the call, but in hypothesis testing, we typically set out to see differences. Here, we're going to flip it on its head and say we're setting out to see equivalence, And one way to show it here is in terms of the alternate being in terms of absolute value of difference, not caring about the direction that we're going. But we also might be thinking about a particular direction where the sim is greater than the live or the live is greater than the sim. So we're showing you two different approaches here. But bottom line is we want to show equivalence. We want to prove or have evidence for equivalence. So the approaches that are out there have been used in other industries quite successfully over time. One method is using a confidence interval approach. And as you see down there, we're going to build a confidence interval on the difference in the averages and then see if that confidence interval, both one-sided tests are rejected. The confidence interval is going to be contained within this plus or minus delta interval. And delta ends up being a big deal because that's really what we need to specify up front as our comfort level with if they're different, how different can they be and we're still okay with it. All right, 0 is perfect, right, in terms of equivalence, but we can deviate, and we should, from 0 and come up with some notional delta that we can allow for and still call equivalent. And the more common approach, at least what's currently used, is this 2 one-sided tests, or TOST. Jim's going to get into a little more advanced method going forward, but basically available in standard software. This is screenshots from JUMP, and you can see that for the same data set, I think we had about 31 observations for each of the data sets. Again, thinking about notionally as a live data set, a referent data set versus a simulated data set, that depending upon the delta we come up with, we might say that we're equivalent or we're not equivalent. For the smaller deltas, it turns out that it's harder to show equivalence, and that should make sense, hopefully intuitively. And then, so a larger delta, we're showing here the same data set, but using a delta of 0.25 versus a delta of 0.5. And for 0.5, you're seeing that the p-values have some color to them. Both of them do, and max over both as well. And so as a result, we're saying that we're by saying we're significant, less than 0.05 and greater than 0.05, we're showing equivalence for 0.5 delta. For 0.25, not equivalent. So more to come on this, but just one standard test showing equivalence. We have data we're not necessarily saying where the data was born out of in terms of conditions, assuming similar conditions, and really not trying to learn necessarily anything from what's going on in terms of the settings of the system, either live or simulated. Another very, very common approach is Kolmogorov-Smirnoff Test. I saw John Heyman mention this morning in some of his advanced methods. Very, very commonly used for looking at distributions of data, live versus simulated. And it's a non-parametric test, so we're not assuming any sort of underlying parameters or distributions. And we're just doing essentially a distance test to determine whether or not we're statistically the same or different. Same or different. And just another example came from JUMP here in terms of detection times of a missile warning system. And I really like the CDF plot. The compare density is not too bad. They look sort of the same, but sort of different as well. But if the lines are sort of coincident on the CDF plot, that's an argument for similarity. And it also shows you the test statistic that's used for a KS test, where we're looking for the maximum deviation across the CDF as it's growing from 0% to 100%. And the cutoff there, or the point of max difference, is there a detection time a little greater than 2.5. Okay, and then a statistical test is performed on that. And the idea is that the alternate hypothesis is that it's different. The two distributions are different. And so a p-value that is small is a declaration that the distributions are different. So if we're trying to show similarity, then you're trying to essentially look for a larger p-value. And then one that's also quite commonly used in modeling simulation, which is sort of a combination to some extent of the equivalence test and the KS test here, is this Fisher's combined probability test, where we're going to look at test by test point by test point that we get out of live testing, which usually is very, very, very expensive. You show an aircraft there trying to hit an air target, and maybe some end game kind of flyouts of missiles for a given geometry of that missile close to the target. Or what we've got there in terms of yellow dots is all the results that we got from modeling and simulation here, from Monte Carlo seed, different seeds, and run the simulation a whole bunch of times, versus the red dot being the one result that we get from live testing. And we want to compare where that red dot lies relative to the density of all the simulated points. So what we're seeing down here at the bottom are different tests, not different tests, but different live shots that realizations that came out. And then for each one, generate the simulated shots, the blue dots, and see where the red point falls within the distribution of the blue dots. And that p-tail is giving us a sense for that. And if you can't read them, I got my glasses. And for p-tail values, if the red dot is right in the heart of the density of the blue, you're going to have a large p-tail. Whereas if the red dot is quite a ways from the density of the blue dots, your p-tail is going to be quite small. So if we look at the second one, top row, second one over top row, that's one where the live agreed quite nicely with the simulated. And then you look at the same second over in the bottom row there and see that the live is quite different from the simulated. And then the Fisher's combine is to aggregate all this into a single statistical test, and uses the test statistic, which is a -2 log of the probabilities of the p-tails, if you will, and comes up with a single test statistic and then chi-square value. And same sort of idea with the statistical test here, is if you get a large p-value, then you're going to be essentially saying that there's no difference between the simulated and the live.
Hey, Jim, question in the chat. Are the
Thanks.
probabilities of likelihood a live test point falls in contours of some of the simulation done by profile likelihood?
Profile likelihood. No, I'm drawing a blank there. So I guess and maybe just a rewording of the question, but essentially the idea is if we know the setup of that live shot, then we would get all the parameters of the live shot and feed that into the sim and run the sim under those conditions. Does that answer the question?
Nothing else from them, but somebody in the chat also said that p-tail is the percentage of the point that fall outside the live shot.
Okay, yeah, absolutely. Absolutely. Yep, better way of saying it. Percentage of points that fall outside the live.
No.
I'm hearing someone else. I'll press until we get maybe another question then. Just some things about Fisher Combine can be used, encouraged to be used when it's a go-to, need to. But generally speaking, we only get it's sensitive to a single low p-value that can drive that test statistic. So it can be influenced by, what we would call an outlier type of thing. Probably the biggest disadvantage is that we're not thinking about any sort of factor space or factor conditions when we're doing Fisher's Combined, and we're just sort of picking shots as we get them. And so learning about the factors is something that we would want to do, and that's sort of where we're headed in terms of talking about test design to enable us to be able to do that. And just, this comes from the MISCO, but is now called Modeling and Simulation Enterprise. It was a coordination office for defense, has a great resource bank there for us to leverage. You can just look it up online and go there and take advantage of all the resources that they do have there. Would apply to a lot of different organizations, but validity, is dealing with sort of this triad that you see here between a conceptual model, what we end up with in terms of non-sim computerized model, and what's called the problem entity, which is the live space or the true system under investigation. And so we're going to be bouncing back and forth between, particularly here, looking at experimentation and being able to do some comparison between computerized and the live system under test, doing some analysis and modeling, going back and forth between the conceptual model and the computerized model. A lot of arcs there, if you will, to be cognizant of when we are working on the V&B problem. Right, we've got variability that's present, and if I could only spell statistical, we'd be all right. But statical is fine. But the idea is to have this capability from a statistical analysis and statistical test design perspective when we've got a system that in real life has a large noise component and may have signal due to factors that we're changing. So what we like to do on the analysis side, once we have data to collect, And analyze is to be able to parse out the signal from the noise. That's one of the challenges in statistics. Noise can be reduced to some degree by sample size. Larger sample sizes are better. In many simulations, we can take advantage of that with the ability to run simulations in a fairly short order and run many of them. Sometimes we don't have that luxury, but at the same time, more is better, generally speaking, for managing noise. But the noise is the noise a lot of times, and sometimes it can be overwhelming, particularly when we're restricted on the live side of the house of only a few shots that we can do. So speaking of that, when we go to exercise the system or system of systems and recognize that we have a fairly large operational envelope, what we typically find is that if we're only going to do a limited number of investigations and we want to fill this operational space, we've got difficulty environment, difficulty in the mission on our axes here, that it would be perfect if we have just a few, like 5 different live test points to put them across that operational envelope. But we don't necessarily have all the resources or the ability to set that test range wherever we're going to be testing completely operational. And as a result, we test some slice or small piece of that operational space in live, and then rely on the simulation to come up with coverage of the rest of the space. So intended use is thinking about going after the situations where we can't get the live test data. But ultimately, we'd like to be doing some heavy lifting in regards to taking advantage of this live data and using it for V&V purposes. Okay. One example, this is from small diameter bomb, but we'll talk about this case in just a minute. But say we've got 12 factors and we want to cover some big space for each one of the factors, right? Potentially, sometimes maybe not. If a target type, there's only 2 target types, so we're good to go. Then, but if we have more than that, boy, we're going to start growing the operational space. What we're attempting to show you here on the right-hand side is dimension reduction first from 12 down to just 6 factors. So take any 6 of those, label them A, B, C, D, E, F, and then say across that 6-dimensional space, we're going to look at 2 levels of each factor. And if we look at all those combinations, that's 64 points. Problem is, you grow that to 12 factors, there are over 4,000 points. And if you go to 4 levels of each of the 12 factors, we're at 16 million. So a challenging problem in terms of covering the space. We'll see in the case study, maybe there's some alternative approaches from a test design perspective that we can use to benefit our reality, which is limited resources. So if we think about going into this M&S underlying system, this is for air-to-air, probability kill. Certainly that was something we looked at in regards to the Fisher's combined situation, right? Miss distance, probability kill for missiles intercepting threats, certainly one. If we've got that type of situation, what could be going on with the simulation versus live, and how do they relate to one another? So this is a chart that's trying to accomplish that. Up there at the top in that rectangle, you see that we have notionally the true system behavior, and ultimately we're trying to get that every time that we go out and test. We're trying to capture true system behavior, but recognize that even live testing, as operationally realistic as you possibly could get, is an abstraction, because we're using training assets or we're using some mock-up of the target, or whatever it is. It's not the true system in its environment with all the different parts and pieces associated with it. So we're going to have some abstraction. We're also going to have noise present. Those are the blue clouds. So whether we're going to the left of the slide, down the center, on the right, we have noise. It's present. What I'm going to try to do here is parse what we see over here on the right-hand side, starting with the pictures. That's really what we're getting in terms of reference information. And then over here on the left-hand side, we've got the sim that's being developed. And the sim might be subdivided, can be subdivided a lot of different ways. But one way to think about the sim is things that feed the sim. One is reference data. Other is component models that we need to build from scratch. Other models that we pull from other simulations that are almost form, fit, function, just plug them in. Other things coming into our simulation, Monte Carlo variables. Almost every model, and some models have dozens, if not 100, Monte Carlo variables associated with it. And what I'm assuming is we have models that are making up some integrated simulation, What's another input to the simulate? Well, underlying physics, right? And we're checking physics against what the simulation is coded up to be or doing. And then we've got agile present, and agile is a process, right? But if that is part of building up the simulation, how do we leverage agile? How the software engineers functioning relative to the other technical engineers that know the underlying system, the physicists and so forth, the analysts, how they all working together. Ultimately, at some point, you're going to be thinking about that simulation. You're going to be thinking about a test design for the simulation. And then all along the while, you're going to be doing some component or bench testing that are going to feed the individual models. And so this is lower level sort of referent, if you can think of it that way, or tiered sort of referent, tier 1 referent. And then we can move up to a subsystem level and do, this is captive flight test. So put this weapon right on a helicopter right here and just fly it around and collect all sorts of data. And then finally, we're going to fire the weapon. This is ground to air. You can have air to air, you have air to ground, whatever you want, for whatever system you're going to be working with. For each one of those, you're going to have test design that you're going to need to be contemplating, constructing, and using for the best purposes you possibly can going forward. So if nothing more in terms of a message from a test design perspective from this session, it's that we need to be thinking big picture, and then we need to drill down and be very efficient and effective when we're going through the design in the sim and design in live. And this is just more thinking about that from a V&V perspective. Now the inputs are these individual models, and those are the different components of the sim. And then we've got these other little subsystems we think about on the live side, down at the lowest level, the subsystem level, and the system level, and what feeds those in terms of tests we do. And then all the while, what do we want to be thinking about from a V&V perspective? Generally, from a test design, we think about it in terms of plan, design, execute, and analyze, and make that sequential so that iterates. But ultimately, at the end of the day, we've got a test design we need to deliver over here at the 3 o'clock. We execute that test design. 6 o'clock, at 9 o'clock, we analyze data, generally speaking. And then we want to invoke that across the entire acquisition lifecycle so that we're seeing what is going on holistically, and that we're getting information fed from early DT to mid DT to integrated DT, OT, all the way to OT, and playing the team approach as we go along. Another way to think of this framework, and thanks to the Ida Kelly especially, Laura Freeman thinking through this, coming up with their handbook on M&S. #1 reference that we would recommend for stat methods for M&S V&V. But bottom line here is if we think about the M&S generating ultimately a statistical emulator, a statistical mathematical model from the M&S after you've interrogated the M&S that we can then compare to the live testing. And out of live testing, we're getting a statistical model for evaluation. And hopefully, as you see there in the bottom, we've got some common parameter space that we're dealing with on a particular program right now for DoD, and we're calling it a global factor space, but that is something we're fighting all day long, all week long, all month long, whatever, year to year, to make sure that there's agreement in terms of what are all the different factors associated with live, associated with the M&S in particular, that we want knobs to be able to vary, to turn, and see how that ultimately affects overall performance. Yep, culture change. Yeah, I can't say that enough, right? Things that you know, if you're attending this conference, more than likely you've got a leg up on the statistics side of the house, taking that, leveraging it within your world to make a difference. And sometimes it takes more than one discussion on the same topic. Just get off the stage. I see I got about 7 minutes, Jim, and might give you back a few of those here as I go through this example, just to look at sort of start to finish test design to analysis, not necessarily focusing on the equivalence KS and Fisher's combined so much, but more on this holistic statistical modeling approach because we have factors involved. But here, let's look at SDB2, current program, small diameter bomb, multi-service weapon, air to ground. It's a glide weapon, but very, very accurate. 3 different modes associated with it, sensor modes associated with it, but not a bad cartoon there in terms of what it's trying to accomplish and the various different communication routes that it takes to get there. Here's an example with 6 different factors. So sort of initial conditions kinds of things. Looking at the angle of loft, where we are in terms of cross range and downrange, elevation above the target. No, I'm sorry, elevation above the target is altitude, target elevation where the target is elevated, and airspeed. And then things that we're going to measure on the output side. And the thought behind this is we're going to run some simulation runs, we're going to run some live testing, and we'd like to compare the two. And we want to be very, very efficient and effective, right? So we went through a sequential approach, 2 phases here, where the first phase was a fractional factorial 16 runs in 2 levels each, and just a geometry of that 6-dimensional space there in the top half. And then the bottom half is an augmentation to a 5-factor central composite design. And didn't do total justice on the diagram there because we don't have that many axial points, and they're in the wrong spots. But bottom line is we augmented it to a reduced dimension 5-factor space with 3. I think we had 3 levels face-centered central composite design for this particular example. And then the idea is to take the results that we had from live, build a statistical model, take the results from the sim, build a statistical emulator, and essentially compare the two. And so the top portion there is output from a statistical model in terms of the coefficients and their estimates. And then the profiler showing the influence of the individual factors. And ultimately, if we did this dynamically, you'd see that there'd be interactions that the slopes change as you change the levels of a factor. And here showing 3 factors that are highly influential: altitude, airspeed, and target elevation. And that was true on the live testing. And then you go down to the simulated. Confidence interval is a little bit lower. Okay, more runs run there notionally because we can afford more runs. But ultimately similar kinds of findings, maybe not so much on target elevation, but and maybe a couple of these other ones that are more mild, but not too bad in terms of types of results that would start the discussion on whether or not we're valid with the simulator relative to the live findings that we're getting from the real data. Off the stage. Sort of the why and the statistical methods in M&S VNV. We started sort of scoped in terms of the, well, we went definitional in terms of the process, right? But then went scoped in terms of statistical methods to feed what Jim's about to talk about. And then went sort of big picture on test design analysis, which is really a theme that we try to hit every chance that we get in regards to good standard practices for statistical method application for mod sim VNV. Random variation, recognize, discipline needs to be efficient, cover the space, maximize knowledge gained. And then on the how, use experimental design statistical analysis methods. Classic experimental design might work for small run types of situations, but we need to be thinking outside the box a little bit in terms of space filling and what we call hybrid designs for large run simulations and that type of thing. And then develop this rigorous approach statistically based for simulation VNV. And then finally, trying to make sure that the methods that we're employing are accepted on every side of the house, whether it's on the producer side of the house or the consumer side of the house, however you want to view it in acquisition. Make sure everyone's committed and agreed upon. That's the way to go.
So hopefully I've taken control and have a different set of slides up that are the same. Thank you all for being here. First and foremost, as Jim was working through a lot of that material, I was scanning, looking at all the folks in the participant list, and it's very regrettable that we're not together because a lot of great discussions occur, as you know, during these meetings. Not quite the same as the Zoom virtual, but hopefully next year we'll be together and can share some of this information some more. So what I'll do is I do have a little bit extra time, so maybe I'll show you real quick how you might do some of the things in a software package, and we'll use JMP. I know a lot of you have that. And certainly some of these methods will be implemented through Python and R as well. But I thought I'd kind of show real quick some of these ideas and then go into, well, how can you show that curves are the same? And then I'll kind of take in a completely different route here and get more into the design phase. As Jim had mentioned, you really have to think up front in the planning and design phase as to what you want from your tests, right? So if you don't set yourself up to have that common parameter set, for example, you're never going to get there from here in trying to do that comparison. Is my live equal to my simulated, to answer that question? So let me, I just kind of, while he was talking, I kind of came up with a little toy example here in JMP. So what I've got is I've got 30 live and 30 that are simulated. And the question is, are these, are they equivalent or not? So if I come under a fit y by x, I can go ahead and put in the responses y and the factors x. And then from here, we can see the plot. So in general, it looks like the live 30, and again, this is relatively simple in that I don't have the factor space that Jim had mentioned when we're talking like the STB2 example, but here it's just, is the data equivalent to each other? And that's going to be an important distinction. Is it's nice if you have the data equal to one another to maybe give you an idea the simulated is equal to the live. But often we care about is the characterization the same, meaning is the impact and influence of a factor equal in the live as well as the simulated. Kind of like in golf, right? There's lots of ways that you can shoot an 80, right? Either you're really good at the putting or really good at the approach or really good driving or some combination thereof. But we want to know, is it consistent across the two environments? So clearly we can quickly do a t-test and say, life is good, I'm done. They are equal because my p-value here is less than or greater than 0.05. So we fail to reject, so they're equal. But we all know that that's not quite right, and we have to maybe take the next step and do what Jim's talking about in terms of the equivalence test, where we're saying, well, what difference is it that you think is different? Or practically, and this is where you take your hat of statistics off and put on your operator hat and say, what is meaningful to me? And I'm going to say there's a quarter second. We'll say that this is in time. So then I get this output, and the question is are these equivalent or not if the difference I care about is a quarter second? And we can see in this particular case, because it's blue, I cannot declare equivalency. What happens on this TOST test, two one-sided test, we have failed. So in other words, I'm 99% confident that the difference is at least greater than on the low side, right? So it's the high side that I'm a little bit off, right? So if I look at the difference here, 0.11, I'm 99.99% confident that that's greater than negative 0.25. But here, I'm not quite so sure that I'm less than positive 0.25. I am less, but I'm not statistically significant in that difference. So if I go ahead and maybe change that idea and put it into maybe 0.3 seconds in my reaction time, whatever my response happens to be, now I catch them both. Right, the difference has not changed. It's still 0.12 or 1/8, if you will. And I can see that I've kind of got statistical significance on both sides. Now, we also mentioned that there are many other ways to look at equivalency in terms of we can do a, let's see, under compare means, we can do some of these guys, and under non-parametric is that Kolmogorov-Smirnoff test, and we can get that answer right here, where you have your overall p-values and saying, do you have equal distributions here? And again, that whole idea is based on looking at the CDF plots, which we can do under CDF plot right here. So we can look at that. What's the max difference between these cumulative distributions, kind of thing. And then there also was some densities, and we can kind of compare the densities and say, you know, okay, it looks like they kind of follow one each. So is that different or not? So these are some tools that are kind of quickly available for that, that first check, if you will. So now kind of transitioning back to the script. Imagine that I went off the script. Now, what happens when we're trying to prove some level of equivalence in curves? This is not uncommon. So we run across this issue in many different applications, whether it's testing and you have your instrumentation, you're getting observations, on 30 per second or whatever it happens to be, and you're looking at what is the performance over an interval of time. So not uncommon that we see these type of applications where we're looking and trying to establish equivalence in these two curves. This particular one is an example from this semiconductor industry where we're trying to say, are we getting that, is that max the same or not? That's an easy question, right? If we just look at what's the max delta, we can do that with the two sample t-test that we're just doing now. But if I want to model the entirety of the curve over the time domain, that's a little bit different question. Now, we could take certain chops, and then do like a matched pair along the way, and that's perhaps an idea that could work if you take it at every 1 second and then see are all of those points equal to one another. So not a bad idea to do a paired t-test is what that would be called. But if we truly want to capture the smoothness or that linear behavior, there is something that's called functional data analysis. So we want to capture are the functions equal to one another. So very different idea here. So probably easiest just to kind of go through an example here. So a lot of work we've been doing lately is with autonomous systems, huge push in the Department of Defense for obvious reasons. So this example is just going to be using the Tesla AutoNav system. So the idea is as we look to many different factors, do we have something that's changing the probability of collision? So there's going to be 100 different runs doing some highway testing, looking at the lane changing. So you can think of all of these as each run having different input settings, i.e. the speed that the Tesla's going, the oncoming car speed in the left lane. So the idea is we're going to merge to the left. And then maybe the aggressiveness setting that you have on the system. So you actually can put in Mad Max if you want to be quite aggressive out there on the highway and test the patience of your fellow drivers. And of course, other things that could make a difference on the probability of collision would be how dark it is out and the wetness if it's raining. And then there's also the degree of autonomy, right? How much input do I have? Like I'm going to put my hands on and say, no, don't do that, Mad Max. So again, these are different probabilities that I look. So this is over a 12-second period. What is my probability of collision? And you know, we can see that there's some areas where you have very high probability. And then some of these curves, like in curve 16, we never really have much chance of having an accident kind of a thing. So the question is, how do I model these curves over that 12-second period and kind of establish, well, what is the influence of each one of these independent variables? Clearly, I could say at the 6-second mark, what is my probability of a collision? And I could do standard analysis that we do for DOE. But I want to know over the entirety of the epoch of the 12 seconds. That's the question of interest. Fortunately, there is a technique called functional data analysis, and there's a few steps in there that you first, not uncommon to any analysis, you got to do your preparation and cleaning the data just to make sure that all of your probabilities are between 0 and 1 and everything is standardized and you're ready to do your work. And then in this functional data analysis, the next step is to kind of fit splines to the data. So in other words, you're going to kind of partition over the 12-second interval some sub intervals in there that you're going to say, okay, from 0 to half a second, this is a spline that is going to explain that behavior. So we go ahead and create those. And then from there, we're going to go ahead and do a principal components. We're going to create functional principal components from those eigenfunctions with the hope, of course, being that we're going to be able to well represent these curves via these functional principal components. So for example, if I look at run number 13, okay, I can see that basically I have from 0 to 11 seconds, very small probability, and then I have a pretty good probability at the end. And that's a lot like 19, right? So 13 and 19 curves are very similar to one another. And then I come up here and I look at my eigenfunctions, and these are the things that I can kind of piece together and play with to try to model the curve. In this particular case, because I've got the big jump at the 11-second mark, I can see that that's kind of like eigenfunction 4, where at that last point I've got a spike. Of course, I'm kind of going the opposite way, right? So as it turns out, if I look at run number 13, I've got a very high negative value for FPC4. Similarly, for 18, I've got a very high, or 19, I should say, I've got a very high value there as well. And then when I look at a scree plot, I can see that 13 and 19 sort of between FPC4 and FPC1, that these guys kind of stick out. But bottom line is I'm using these eigen functions to kind of piece together so that I can represent the curves. And there's going to be weights as to how much of each function that I need. So then from there, I am able to go ahead and fit these curves using generalized regression, whether it's adaptive lasso or any of the other methods out there. that you can see here under your estimation method. You have many different choices. So now I'm able to go ahead and figure out over time, if I want to minimize or maximize, I'm able to do that. So that's kind of neat that I can represent the curves through these eigenfunctions up here, but that kind of only goes part of the way for us. So there's kind of two missing pieces, right? It's great that I've got a model that I can model any one of my 100 curves, but what I want to do is two things. One is I want to translate that into real life. Great that eigenfunction 4 is real important, but what does that mean in terms of the speed of my car, the speed of the oncoming car, the Mad Max, or am I being timid? How does that relate? And more importantly, since we're talking mod sim B&B, how can I come up with like an ideal curve that would well represent, and then how do I get those settings so that I can be on that ideal curve? Or in our case, where we would say we would be able to compare that this curve is in fact equal to the other curve. So with that, I would like to go ahead back to jump and maybe show how this would work. So I'll kind of pause a moment here and let you chime in with any questions as I bring up the example. So this example has 10,000 rows, and what you'll note is there are about 100 rows per trial. So you can see as I transition here between 101 and 100, now so all these runs, the first 100 are all at the same setting. But I am taking I'm finding the probability across that 12-second period. So you kind of see that time is increasing over that 100. And then I got my collision probability, and I have the settings for my 4 or 6 different factors in here. And then the hope is I'm going to relate those factors to what's my collision probability. So to do that, I can come under Analyze, and it's specialized modeling, and this is Functional Data Explorer, which is Jump Pro only, I believe. My output of interest here is that probability of collision as a function of time. And then I have to put in the trial as an ID function that tells me, okay, here's 100 different runs, kind of a thing. And then my supplementary variables are going to be these guys here, disease. So I'll go ahead and hit OK. And there we have. Looks like I must have had one. So there's the 100 different curves, you'll note. Hopefully there's not too much of a lag or a delay in here. But you'll note here are my curves, and then the first step is going to be this whole data processing or data cleanup, which I've already done, but just to kind of show here's some things that you might want to do, and then transform a line. And then this is where I want to load a target function. So what I'm saying is, what one of these curves out here do I want to determine how different am I, or how can I emulate that particular curve at a particular time? So if I want to be at the 6-second mark, and I want to be on the curve, and again, the curve may be the simulate or the actual live or simulated, however you look at that, you go ahead and select it. So let's, for sake of argument, we'll say 19 is what we want. So I'll go ahead and put right here in my target function, I'll go ahead and load that I want to replicate. So goodness to me, okay, is going to be 19, we'll say. And I know realistically that's probably not what you want. You don't ever want a high probability collision, right? But for the sake of R&D, we want to kind of dig deeper as to what's causing that big spike at the end. So now I've got the target in there, and I need to go ahead and fit my my splines. So I got a couple choices in here. B splines are mostly used. You can do P splines if you have really complex behavior, or Fourier if you have seasonality type things going on. So now I'm fitting the splines to these models. And it kind of gives you, you can kind of see how many knots, which again are going to be the partitioning of the data across your time domain. The recommended number of knots here is going to be 9. So with that, we then, let me get this out of the screen. We then come over here and we see that we've got the eigenfunctions, and we've got 6 of them, and then we got a nice free plot over here that suggests, you probably don't need all 6, because I can get 95% of the overall variability in these curves with just the first 4. So let's go ahead and customize my number. And I just want the first 4 principal components. And there I have it. And then you can see that 94 and 68 in component 1 and 2 are kind of outliers. We could go take a look at that, but in the interest of time. So here's a profiler. And the profiler is in terms of the functional principal components over time. So we can kind of see we can model that collision probability as your functional principal components. And we can do, for those familiar with JUMP, you can do all sorts of important optimization here and figure out, well, how can I minimize probability at time t equals 6 in the principal component space? Again, to me, that's maybe in the black box world, but I want to know, what does it mean in the real world? So that's where we're going to transition up here. Under where it says B spline. I want to transition to functional design of experiments analysis, such that I can now understand that in terms of the real things that matter to me, that I can measure and understand. So it's the timidness factor, the lightness, and the dryness. And we can kind of see, well, what is it that is influencing my collision probability as a response? But don't forget, our whole goal here is to say, do we have equivalency in our curves? So that's why we already have automatically for us, because we loaded a target, we have these responses created for us. That's going to be the difference from target 19 or the integrated difference from 19, where you can kind of figure out, well, what is the true players here, right? At time t equals 6, we can kind of see that speed is very important, and then that timidness factor. But you can see where you have pretty robustness to the situation. So if we wanted to, we can put on our desirability functions, and then we can just go ahead and maximize the desirability, which will give us the optimal settings in terms of, okay, if you want to minimize your error, here are the settings that are going to get you closest to your ideal curve. And again, that ideal curve being what your simulated value or your real value, whatever you call your referent, is. So kind of a couple different philosophies, I suspect, there, whether you want the simulated to be the baseline or the real to be the baseline. To us, we typically like the real if we have enough data to be, here's what is true in terms of performance. So that's some ideas in terms of your ability to model curves.
Hey, Jim, there was one question, if you've got a moment. So Craig Andres was asking about smoothing needed to compare curves. So he said, you could use cross-validation, but that sometimes overfits. Even so, if you could use the same level, should you use the same level of fitting for 2 curves you're comparing? Or does it make more sense to decide the level of resolution, sensitivity you want the curve to have, and then standardize the level of fitting?
Yeah, absolutely great, great concerns. And to be honest, it's a great, great for you to try multiple different ways and looks at this to see if you get consistent results across those ideas. But absolutely a fan of holding out of your 100. Are there some smart numbers that we can hold out and then create some of these, because we can save the prediction formulas on these functional principal components and then be able to do the prediction. And then, like at any other type of analysis, determine how far off is our model when we hold out some specific things. And of course, you write a script to kind of do that autonomously or automatically, so that you're holding out a different group. So if you want to hold out 5 at a time, 10 at a time, and then just randomly do that. So.
And one other question just came up. This is from John Heyman. What's the advantage of this functional data approach with eigenfunctions versus a standard regression with splines?
I think in terms of being able to have some level, for me at least, of how quickly you're able to create these basis functions that are kind of automatically figuring out where those knots are, and then from there taking the subspace. So in other words, if you're doing regression, you kind of have to do more of that variable elimination step and whatnot. But here, your eigenfunctions or your eigenvalues and eigenfunctions can kind of quickly come up with the orthogonal components for you. Again, like all things, you have a couple different ways to get at it, but this has proven to work out pretty nicely, particularly given this latest translation step. I think they put new in jump 15 maybe, where you're able to go more easily into the functional DOE. Okay, so let's let me see if I can find where I was. Now let's transition here totally. And by the way, you can do some really neat things and kind of figure out, well, what are the of the 100 runs, which ones are like each other by doing some cluster analysis on the functional principal components. And then you can kind of see, if I have the 4 functional principal components, we can see that this group here has very high levels in functional principal component 1, and then maybe these are grouped together because of the FPC4, and I could kind of see, where all these come out in the constellation plot. So lots of analytical ends once you get your functional principal components. Okay, now switching gears. So we've been talking about really the analysis piece, right? So now we have been talking modeling and simulation, and back to the idea of autonomous systems. What we've noticed over the years is that there is a very common characteristic as we do these models and testing, that autonomous systems kind of have what we call boundaries. In other words, they don't necessarily have nice, smooth performance in the response over the range. They have kind of like maybe some cliffs, and these are called boundaries. So what we want to do is be able to effectively find these boundaries after we've done some simulation runs, and we want to augment. So if you think about some of our systems, particularly these complex MDAP, major defense acquisition programs, you're going to have some simulation that's going to be needed kind of real time. So I need more runs, give me more runs. Well, which runs should you be giving them? Well, we believe that it would be useful to do some runs where the action is. So if you have some parts across your response surface that are well defined, then you probably don't need to spend a lot of extra runs defining well-defined more. So why don't we go where we have a bit more uncertainty? So the idea is we want to augment a design in an adaptive sampling idea here. So given I have some information and responses, where should I test future runs in a ModSim environment? So if I were to go to standard DOE software, and again, we'll use JUMP just to stay consistent here. If I want to augment a design, so I've got my, whatever, 400 runs from my ModSim, I want to do another 100. My choices are all limited to focusing on the design space. So you can look at whether you want to do replicates of things that have already been done. You can do axial runs or space filling, as it turns out, many of you know, is enormously useful and powerful. And in particular, had some nice developments recently, being able to incorporate not only categorical factors, but constraints as well. So great space filling capability that we use in the ModSim world. But again, it does not pay attention to what's going on with the responses. And then even in the augment, you can choose what optimality criterion you want, but that's still, those are all based on your information matrix versus your response. So what we did is said, there's a lot of folks out in the community that may be interested in sampling versus using inputs from the response. So maybe before we do that, here is an idea of a gap filling design. So what happens is these are my input variables, x1 and x2, and this is an extreme example, I get it, but you can see there's a hole here, right? And there's a hole here. If I sample more, I would like to fill that hole in, right? Now this, I get it, is extreme, but once again, if we think of large dimensionality, we have the curse of dimensionality where we do have big holes out there. So let's try to fill in the holes with our new runs. And this, again, has nothing to do with the response yet. So this is kind of a stepping stone that we came up with as we were trying to learn more about this. So here's what you would do if you did a space filling. You could see for example, there's probably 800 points here. And if I add 200 more, the blue ones are where they're going to come in, which on the surface looks like a pretty good fill. Right, so I've kind of got this filled in, but then you go ahead and take off that coloring, and you can still see that you got some issues here. That if you had 200 points, you really don't need more up in the the corners. You need them in the middle. So can we figure out a way to kind of focus toward the middle? And that's called a gap filling design. And we let's see, I'm up against time. It looks like so we're good till what, 1 or 2:30. So 1 to 2:30, yeah, okay. So I won't demo this real time, but we have an add-in that happy to share, and all we have to do is just say, go ahead and fill that gap. And you can see these blue points now are the gap filling 200 points. Again, same number of runs, but only more directed at the holes. And you can see when I take off that particular coloring scheme, this looks a lot more uniform in its density of the gap fillings. So what did we do for the gap filling? Essentially what we did is we just smeared like 4 times the number of runs in space filling. And then we said, hey, if the idea was if you are an existing point, we'll give you 1. If you're one of these new like 4x space fillers, we'll give you a 0. And then ultimately what we try to do is predict what's the probability that I'm a 1. And then that allows us to kind of rank order. And then the points that are farthest away, as in the probability of being a 1, those points are going to be what we find are going to be the gap filling guys. So turns out to work out pretty well. And here's another example. You can see the cylinder here in 3D, and then I go ahead and put in some of my gap filling points to fill that in. So now you can kind of see that has filled that in well, particularly when I take off the color. But that's a piece of where we're going. So back to this idea of we want boundary points. So points on the boundary, and we want to know how do we do the adaptive sampling for autonomous systems. So here's the current options to our knowledge. There's some great work done by the Applied Physics Lab, the folks at Johns Hopkins APL. They have a tool called RAP, Range Adversarial Planning Tool, which has a lot of thought put in it to kind of figure out this exact same problem. Understanding that we're testing a very complex simulation system, kind of need real-time updates to it. So how can we do that? They've written a few papers out there, and I got to work through some of that and worked with them to know what they're doing. And I thought to myself, I can't necessarily get to the level of complexity that they're doing. But then again, they are to use this tool. It's going to take a little bit more that the average test team wouldn't have that resource available to them. So is there a way that we can kind of come up with algorithms that the test teams and practitioner have at the ready? So that's where we said, why don't we use some of the native capability in JUMP, and we can generalize that to R or Python, whenever we need to do, and then see if we can at least get a decent solution. So we kind of used this as a bit of a source document, and we took a lot of different turns that were, one, because we saw performance was better doing it a different way, and two, that we didn't necessarily have some of the capabilities that we wanted. So here in that paper, they kind of give this as an example of where you would want to put these new points. So if we can kind of go back to our same autonomous navigation example, and we could even maybe think that on the x-axis here is your speed, and on the y-axis is maybe the distance away the car is. And we can see that maybe down here in this particular region, we have a low probability of an accident versus maybe up here, we have a much higher probability. So we have very steep differences, if you will, in the probabilities of collision. When you look at this 3D, you can kind of see that there's some exaggerated cliffs. So this is, as much as it's an exaggerated example, it's not necessarily wildly different from what we face in the autonomous systems world. So how can we put new points that are close to the boundary? So what you'll note is I've got in red here where the boundary is, and then the asterisks in there are going to be where the new points go with the adaptive sampling technique. So we call this the BEAST jump in BEAST mode. Kind of stands for boundary exploration and autonomous systems testing. So it's an add-in, and again, very happy to share this. So we kind of come in under adaptive sampling. You can see that we could also do gap filling, but now I have my initial design and I want to add more points to it. Okay, and then here's kind of an interface that I'll kind of walk through here in a minute. In fact, maybe it's I think we've got 10 minutes. I probably have enough time to take a walk down here in this world. Okay, so I've got initially 500 points. And if I look at the graph builder of this X2 versus X1 space, you can see that it is all quite clear where those boundaries are, because I've got the different colors and different shapes based on what the level or the probability of collision is. So for example, region 1, we'll say the probability of collisions, we'll say 0.2 or 20% versus these yellow diamonds, the gold diamonds up here, you have a really high probability of a collision. So we probably want to have as new points as much on the boundary here as possible. So what we've done is we have our input X1 and X2, and then I've got a random variable that means absolutely nothing to this problem, but just to demonstrate that we need to figure out, well, what are the important inputs that are going to influence the response where we're trying to put some boundaries. So we do a screening, and hopefully we'll screen out this random normal. And then I have two responses. One is the continuous variable y, which is a probability between, we'll probably should have changed it up, but it's between 2 and 10, and also a nominal variable that's between 2 and so they're exactly the same, only one's continuous and one's categorical. But the point being, you can do either one. So the idea is how do I go about doing this? If I come to the add-in, I can come under Boundary Explorer, and I can do my adaptive sampling. And I do know that I want to put in both y and y nominal here. And my x's are going to be all three of these variables, x1, x2, which we know are the only ones that matter. Okay, so I'll put those in. And max number of runs to generate, we'll just leave it at 3,000. We have 500 here, but we're really we'll just leave it there. Now, here's some options. Turns out a lot of times in this boundary world, you want to kind of look at the global min or max or some sort of a target that you want to put some additional runs at. And I'm also going to show the intermediate tables that give you a little bit of an idea as to what's going on behind the scenes, because what we're using is a nearest neighbors algorithm, and essentially saying, actually, I probably should get this running because it may take a second or two. And I'll put it in right here. I even have some gap filling runs I'll put in. I'll put in 10 gap fillers for me. So the first step it's going to do, it's going to go ahead and figure out, well, what of your input variables are influential in predicting Y and which one's predicting Y nominal. So I'll go ahead and run. And as it's running, kind of give the philosophy here is what we're doing is we are looking for where we see gradients or differences in the response. And you can see right now that it has the predictor screening out there, and it has found X2 and X1 as statistically significant if I just focus on a p-value that actually will be coming up here. So it's running bootstrap for us. So we got a lot of things going on here to come up with our ultimate number of new runs. So it's still going, but the whole concept is let's look at the responses and try to find where some boundary points are. And there's a couple different ways that we're going to do this. We have what's called the midpoint method. We have let's find some boundary pairs and let's put some new points that are close to the boundary pairs. So we're going to offset it by a certain amount of space. And then we're going to do a bootstrap random forest at the very end to try to see if we can't find some points that are near the boundary. Okay. So I think it's got 1 or 2 more seconds, and then it will tell me, hey, we are done. So now you have your new points generated. And I will say we've tested this and it does scale up pretty well, even though that this doesn't seem to be running so quickly. It's because I have some of the intermediate values that are turned on. So, so here I got my new points have been generated. So I select OK. So first thing I note is it's going to give me this predictor screening, and if I'm looking at this one of Y, I can see that the p-value right here, the proportion, I don't want to use that random normal, so I've done well there. Similarly, I've done well on the nominal response. So now the question is, what happened? So let's look at the real quick. We'll look at the geometry of the new points. So here's 875. So remember I had 500 original. So I'll go ahead and look at 875 all the way up through 500 and see what I got going here. So I will go 502 here. So I can go ahead and look at this graph builder. And of course, you don't see any new ones because I need to get rid of that control panel. Let me get rid of this guy. I'll go ahead and remove. And then now you can see all those black dots are the new points that I just generated. And to be honest, some of them you say, well, why would you have done them down here? That's because those are working on some of the minimums and maximums. And then we also do some larger perturbations, but we want to put the bulk of them on those spines there. So you can see that those 375 new points are kind of behaving the way that we would hope and are going to be on the boundary. So the question is, how did you do that? So what is that algorithm? I'll talk real quickly to that. Maybe we can come back to jump in a second, but let's at least kind of figure out how this was done. Predictor screening is just using random forest, inherent native capability in jump. So what we do is, here's some intermediate output. So if I look at row 1 and I say, okay, what are the closest points to me? And I can see that I've got my nearest neighbors here, my 5 nearest neighbors, and I've got the rows listed. And then I can see, well, what are the distances to those rows? So this ends up being enormously important because I can find now, given that, if I've got row 1 and the nearest neighbor I've got is 78, I go to row 78 and say, well, what's your response? It's -5. And then I go to the next, all the neighbors, and look at the responses. And I recognize that I've got an average distance and an average standard deviation. And if I multiply them together, I get an information number, which then allows me to find out, well, where are the ones that are most different? Where are responses most different amongst those 5 nearest neighbors? And those are going to be the ones that are the highest likelihood of being near the gap or actually near the boundary. So you can see these middle runs here, their responses are all -5. Okay, but so they don't get really any, information, if you will, from them. So hence, it's really the information that is the highest is going to have the most likelihood of being on the boundary. So we end up using a normal 3 mixture to figure out, well, where are those cutoff points to say, is it a high likelihood of being a boundary, or a medium likelihood, or a low likelihood of being a boundary point. So that's kind of how.
Jim,
Sure.
you've just got 1 or 2 minutes left.
Okay, that's perfect. So what happens is then, so if you look at the same thing happens in the nominal world, where we're going to have all these are nominal C's, and then because that's homogeneous, so this particular one with 3 A's and 3 C's is very non-homogeneous. So we're going to say that's a very high probability of being a boundary pair. And then what we do when we find those pairs, we go ahead and take the middle of that, and that's going to be the midpoint. Or we can take a perturbation, meaning if we think 120 is a new point, we just go ahead and move away from it a little bit. So we have the midpoint and the perturbation. It turns out the midpoints end up being more often than not the most useful for us. So you can see that if you look at the blues here, those are really almost spot on the boundary. And then we do the perturbation to kind of explore a little bit away from the boundary. So that is what I wanted to show. But here is just the last example that you can see that if I wanted to put some new points here, the boundaries are pretty well defined here. And then we go ahead and add some new ones, but it looks like we haven't really put anything there on the base. That's because there's actually if we were to kind of rotate it, we'd see that there is not actually any activity going on. There's kind of a channel there. So anyway, a quick overview of how you might want to do adding some adaptive sampling or do new points where you do not have or where you do have information on the response that you want to exploit or integrate into your follow-on runs. So with that, I think I've had enough time to avoid all questions.
I think we've got time for one question, and I want to hit something that Kirsten Meeker asked a little while ago. So she asked, can you comment on frequentist and Bayesian approaches to sample size computation? When should we consider a Bayesian approach for analyzing probabilistic models?
To be honest, not thoughtfully on the spot. We tried a couple different ideas that were kind of borderlining on the Bayesian, and of course, if you think about the Bayesian where you have a prior, that's kind of this idea where I have prior information where I want to take into account that. So not necessarily any great, wonderful insight for that.
Great. And there was one question that came up. Jim, does your add-in work in Base Jump, or do you have to have Jump Pro?
There's the problem. Yes, it is Jump Pro. At the moment, we're thinking that we're going to extend that to other platforms, perhaps.